The last part of our project is creating a filter to fill the song. And first, let us see the GUI for this code, this part of code. GUID news. Okay. So firstly, we create for radio button, which is high pass, band pass, band stop, and low pass. We are going to using 4 different filters to fill our songs. Let's see the code for this. Let's see the first one. The first one is a callback for the high pass button. We first global the value n and y, which from the load button creating parts. The n is the length of y, and the y is from the sample data. We read it from the audio read function. So firstly, we picked parts of the y. It's just a sample data from audio read function. The reason we pick part of y is just when we try to plot the amplitude versus frequency graph. If the frequency is 0, there will be a flat line. So to solve this problem, we just pick part of it. We just use a little bit from 3 of the whole length of y to the 1/2 of the whole length of y. And then we use the ellipse function, which is introduced in the introduction PDF. We look up the ellipse functions in the networks and follow the same pattern as the PDF shows. We pick the order at 6 and ripple at 5 and attenuation at 40, just the same setting as the PDF. And because 0.6 stands for the high pitch, so this is the filter for the high pitch sound. And then we obtain the B and A, which is a coefficient array for nominators and denominators. And then we found we use a frequency function. We use a frequency function, which is also a built-in signal built-in function in the signal processing toolbox to find the endpoint frequency response to the vector and also the corresponding angular. They are used in plotting the magnitude and the normalized frequency graph, which I will show later. So after gaining all this information, wait, there is also a filter. We use the coefficients array for nominators and denominators we obtain from the ellipse function after filtering the 0.6 at our coefficient. We use a filter to processing our y data to gain the amplitude, so we could graph it. We graph it in the area axis 1, which we set it before, and plot it and plot the data. It's just the amplitude we gain from the filter function, and also there is title and label for it. There is time, amplitude, And then for creating the frequency versus amplitude graph in the next part, because we wanted to use the global fs, but the code runs to error. It tells us that it is not fit the longs at the amplitude, so we just we have no choice but pick a frequent unique number, which is most common frequencies is this number as our frequencies, and we use FFT, which is recommended in the PDF to transfer the amplitude time function into amplitude frequency function to calculate the frequencies. We use the NN, which makes sure that the amplitude had the same length at the S, the frequency we obtained. At the S, maybe a negative number, it's hard to plot. We make it the positive non-zero number, and then we plot it and label as frequency and amplitude in the axis 2. Finally, we plot the normalized frequency and magnitude plot in the axis 2 using the information we obtained from the ellipse function and the frequency function. Here, the W over pi is just way we calculating the Nyquist frequency, which we learn from the tutorial PowerPoint and the PDF, which appendix, which tells us the W over pi will give us a Nyquist frequency, and also as the H might be a complex number array, we use the ABS function to calculate its magnitude, and using the decibel conversion to get the x-axis. So finally, we could plot the normalized frequency and the amplitude function. So we can, after showing the code, we can run it to show our 3 graphs. Loaded the music first and play it. And here is our 3 graphs. The one we put in the axis 1 is time versus amplitude, and the 2 is frequency versus amplitude, and the last one is just normalize the frequency with the magnitude. And as we change the button on the radio button here, we obtain the different normalized different figure because we use different normalized frequency in the filter. Okay, that's our analyze